Problem number 44. That's a car, which we will represent as a dot for the sake of expedience. See? All right, we have an initial velocity v naught. Is 4 meters per second, I believe. All right. Now, here's the idea. The car, with a speed of 4 meters per second, is going to go around the loop, and it asks what it's got a minimum speed. So in other words, if it's not going just the right speed, we're talking about another one of those threshold conditions where at the top of this loop, the normal force is equal to 0. I don't remember exactly how they phrase it. Can anybody help me? What the actual phrasing is, why we know that's true?
The car is to remain in contact with the circular track at all times.
Okay, so in other words, we're just going to say if it's got to remain in contact at all times, we're looking for the maximum height. Okay, so in other words, as we make the height bigger and bigger and bigger and bigger, right? As we make this bigger, what's going to happen to the speed of the car at the top? It'll be less and less and less and less. How do we know that? Okay, because the potential energy is going to increase, so the kinetic energy is going to decrease. Exactly. All right, so as we go up in the air, the speed is going to decrease until it gets so small that it can't make it through the loop anymore. So what's the speed that it has to be going just so it barely makes contact? Well, we did a problem like this yesterday when we did the skier problem, right? We said that we could do it as a two-equation strategy, but we could say that mv squared over r has to be equal to mg, right? Because that's the amount of force we need right here is mv squared over r, and it all comes from the weight of the car at this point, right? And so what did we use this for? We took this equation right here, and we got an expression for what? For velocity. Actually, what we did was velocity squared, didn't we? All right, we were able to say that v squared is equal to rg. Why are we just going to leave it as v squared? Right, in the kinetic energy formula, we're going to end up using v squared again anyway, so we'll just let it rest right there like that. All right, so this is one of those situations where we have an energy budget, as we term it, right? At the bottom, or at the top, mgh, h at the top, plus the speed, the kinetic energy due to the speed, one half mv squared, has got to be equal to, so this is at the top, has got to be equal to what it was at the bottom. How do we know that's true? Because what are the forces that are acting on the car as it's going through the loop? Be careful, there's one you might not be thinking of. All right, normal force is the one that's acting, but why do we not care about what's going on with the normal force? It's always perpendicular to the displacement, so no work is done, right? So we don't have to worry about work done by this. Normal force is a non-conservative force, but we know that the work done by it is going to be equal to 0. So here we got 1/2 m v naught squared. All right, so we have a choice here as how we're going to define our coordinate system or what these different heights are going to be. So just to make things easy, what are we going to say this height is right here?
0.
Right, so h naught is equal to 0. And what's the height up at the top in terms of what we're looking for? Because what is the question asking? We've been barreling along, but we haven't really talked about what the question's asking for. What's that? The largest radius, exactly right. So we want our answer to have an r in it, okay? If that's true, then what is this height right here going to be? 2r, excellent. Okay, so here, h is equal to 2r. All right, so we're going to put that stuff in when we simplify this. So that was the top, this is the bottom. All right, since h naught is equal to 0, this is going to go away. And then what we're going to solve for is radius, and we find that right here, don't we? Right? That's 2r. So now we're going to rewrite and simplify at the same time. We're going to leave this over on the left. We're going to say mg2r is equal to 1/2 mv naught squared minus 1/2 mv squared. Everybody okay with that? The algebra? Now, I left out a simplifying step, which would be to cancel out all the m's. So this result is independent of mass. So now there's one other substitution we have to make before we can solve for r, because the substitution includes an r. What was it? V squared equals rg. Good. All right, so now we're going to say that 2gr is equal to, why don't we make it 4gr? Why am I doing that? We get rid of the 1/2. So we get v naught squared minus, what was v squared? Gr. Okay? Everybody all right with that? So I multiplied through by 2, and I multiplied through here by 2 to get rid of those. So this 2 became 4, and then I substituted for v squared, I substituted gr. So now I'm going to have to add gr to each side. So 5gr is equal to v naught squared. So r is equal to v naught squared over 5g. All right, we know what each of those things is. V naught, we said, was 4 meters per second. 4 meters per second. Got to square that, and we'll get 16 meters squared per second squared, divided by 5 times 9.8 meters per second squared, which is going to be 49. So 16 divided by 49, and we'll end up with meters. R is equal to 16 over 49. It's like 0.34. 0.34 meters, or if you prefer, in a more human scale, 34 centimeters. That's something we can think about a little more easily, 34 centimeters. Okay? Well, it's a small car. It's only going 4 meters per second, so it's probably a toy. Okay? Everybody okay with that? So let's take a look conceptually how we ran through this problem. Number one, we had to combine 2 different ideas like we did with the skier on the hill. Conservation of energy and uniform circular motion. So putting those 2 things together, we came up with an expression for v at the top, or v squared, that we could relate to this v down here, and then solve for r, because r is going to determine our change in height. Our change in height is going to determine our change in potential energy, and is therefore going to dictate our change in kinetic energy. That's what's going to allow us to relate those 2 different values. Okay? Pretty complicated problem in terms of the number of things it puts together, but each step is something that you're quite capable of doing.